Good morning everyone. Today we will learn the engineering mathematics and in that we will see the Gauss divergence theorem. Let's see. It states that the surface integral of normal component of vector point function over a closed surface would be equal to the volume integral of divergence of given vector point function. Which means if we have to evaluate the surface integral of normal component of any vector point function, then we can evaluate it by taking the volume integral of divergence of given vector point function. Here is the mathematical statement of Gauss divergence theorem, which is the surface integral of any normal component over a closed surface would be equal to the volume integral of the divergence of given vector point function, which means to get the value of surface integral we have to evaluate the triple integration of the divergence of the vector point function. So to understand this theorem, let us see the example. We are given with the vector point function as 4x I bar minus 2y square j bar plus z square k bar, and S is the surface bounding the regions. These curves are bounded with the surface given is bounded with these curves. So our vector point function is this, and these three are the curves by which the given surface is bounded. And isn't it the equation of circle as x square plus y square equals to r square, which implies here r equals to 2. Therefore the lies from 0 to 2 and z is given as 0, z equal to 0 and z equals to 3. So to evaluate the surface integral of this normal point function using Gauss divergence theorem, this is the mathematical statement. So to evaluate the divergence of given vector point function, we will evaluate it as, we know that the del is it is known as the del, or which is dou by dou x plus dou by dou y plus dou by dou z. So we will operate it on f bar. So while evaluating the f bar with respect to x, the y and z would be treated as constant. Hence it would be 0, and same is for with respect to y and z. So we will get the divergence of f as 4 minus 4y plus 2z. As we got the divergence of f bar as 4 minus 4y plus 2z. So it is evaluated integrate it 3 times, which means the volume integral of the divergence of f bar we will evaluate it as, so firstly we will evaluate it with respect to z, as we are having the limits of z as z equals to 0 to z equals to 2. So it would be the region while evaluating the divergence of f with respect to z, the x and y terms would be treated as constant. So the integration of this would be 4z minus 4yz plus z square, and putting the limits as 0 to 3 we will get this. So the remaining part is double integration of of 21 minus 12y with respect to x and y. So we can evaluate it by using the Cartesian system too, but we will evaluate it using polar coordinates, as we know that to convert the Cartesian to polar we having the formula x equals to r cos theta and y equals to r sin theta, and we replace dx dy with r dr d theta. And we know that our curve by which the surface is bounded is x square equals to y square equals to 4, hence which implies r equals to 2. Therefore r lies from 0 to 2, and as it is circle, the theta would be from 0 to, at it completes it would be 2 pi. So volume integral of divergence of f would become integration of 0 to 2 pi and integration of 0 to 2 of 21 minus 2r sin theta r dr d theta. We replace y by r sin theta and dx dy by r dr d theta. So we will evaluate with respect to r first while treating theta is constant. So the integration would be of 21r would be 21r square by 2 and 21r cube by 3 sin theta with limits 0 to 2. Putting the limits, we will get this value 42 minus 32 sin theta. Let's differentiate it with respect to theta. So 42 become 42 theta plus 32 as the integration of sin theta is minus cos theta. We get 42 theta plus 32 cos theta. And by putting the limits 2 pi and 0, we will get After putting the value, we will get as 84 pi plus 32 minus 32. Hence, the volume integral of the divergence of f would be 84 pi. Hence, the surface integral of given vector point function would be 84 pi. Hence, we use the Gauss divergence theorem to evaluate the surface integral of normal component of given vector point function. Thank you.